So do MS0867, 0950, 1061. So we've seen a sophistication of worms from Configure and Stuxnet to last year we saw WannaCry made the headlines, but NotPetya was probably the most damaging one. Got $10 billion in infrastructure damages. And then just last month, OXOMA came out with a report that said, 919,000 hosts are still vulnerable on the internet. And that's because there's a lot of countries where software piracy is, just the norm, and they don't get things like Windows updates. And so we're still dealing with this issue. We're going to be dealing with it for many years. Another thing is that it's great case studies about Windows kernel's exploitation, specifically bypassing the mitigations that we thought were really good, like ASLR, deb, stack cookies, patchguard, as well as things like patchguard have evolved and generic Windows exploitation has kind of gone away. These show us really great examples of exploiting the driver, using the driver's internal structures during their exploitation. So this is the part where you can boo, because I am straying from the abstract a little bit, and that is because of time, mostly. So I'm mostly just going to be talking about EternalBlue today, but there will be some new info because I haven't seen a published analysis of the EternalBlue Windows XP exploit, which is a different exploit chain from the Windows 7 one, which has been written about. If you're interested in learning about the whole equation group shadow broker saga, you might want to look at Matt Swish's talk earlier this week. He goes through the whole timeline of that. But yeah, I'll just get started. So a brief history of SMB. So it was invented in 1983 by a guy named Barry Feigenbaum working at IBM. He wanted to bring network file shares to DOS. So the first version of it was BAF, his initials. In 1988, Microsoft released the LAN Manager program for OS/2. And that's also the same year that they hired David Cutler, who began work on the NT kernel. From 1989 to 1991, that's when the serve.sys driver was implemented. And that's when most of the eternal exploits, the mechanics for them were introduced. And this was basically just LAN Manager built into Windows NT. 1997 to 1999 is when EternalBlue vulnerability was introduced, as far as I can tell. I could not find it in any version of NT4, but I did find it in pre-release candidates of Windows 2000. And then, of course, in 2017 was when MS17 10 and Fuzz1 came out. So what is a server message block? Basically, it's either going to be a request or a response from the server. It has a very defined structure that begins with the header. The most important part of the header is just what command you want to run. Associated with the command is the parameter block, and this is a fixed size structure. So if you want to think about if the command is to set up a session, this fixed size structure might have things like the length of your username, the length of your password, that kind of thing. And then the data block is a variable length part of the message block, and that's where you get things like the actual password. So there's a special type of SMB, special types of SMBs called transactions, and these are where the data we want to send to the server is so big that it won't really fit in one single SMB. So what we'll do is we'll start a primary transaction saying we have this big chunk of data we want to send to the server. The server will send us an interim response saying, okay, I accept your transaction, send me more data. Then we'll send a bunch of secondary transactions that complete that, fill in the blanks chunk by chunk. And then finally, when all the pieces arrive atomically, the transaction is executed, whatever ioctl command is associated with that transaction, and a final response is sent back to the client. So there's many different types of transactions. There's trans1, which is really old stuff like mail slots. and the remote access protocol. Trans2 was introduced, and that gave us access to doing things on files with greater than 8.3 DOS short names, and it was also part of the OS2 LAN manager. MT-trans was introduced with MT, and the big key difference here was that with MT-trans, the size of the parameter and data blocks of the transaction were changed from a U short to a U long, so more data could be sent over the wire per transaction. So the serve.sys driver has a bunch of dispatch tables that it uses to process different SMBs and transactions. So the main dispatch table would be serve SMB dispatch table. And so when the server goes to process an SMB, it'll look up the command, and then it'll look up that index into the dispatch table and call the callback function. Same thing goes with transactions. They'll look up the transaction subcommands, look them up in that dispatch table, find them, and then dispatch to a callback function. And that's where double pulsar comes in. So double pulsar is the main payload used in the internal exploits. And all it does is it goes and finds the serve.sys driver in memory, and then it finds the transaction2 dispatch table. And there's a function pointer in there that's just unimplemented. So it overwrites that function pointer to a callback function that it created that lets you ping, so you can create a transaction with a special subcommand. And if the backdoor is installed, there's a way that you can knock and see that it is installed. You can also issue a command to exec, which will allocate a buffer and run some shellcode, any kernel shellcode you want. And then you can also burn the implant. So the version of EternalBlue that shipped with FuzzLunch was labeled as 2.2.0. And at the whole heart of EternalBlue is this concept of file system extended attributes. So this is just a hidden name value key pair. It's metadata that's associated to files. It was introduced with OS2 version 1.2 with high performance file system. Windows NT also has, the NT file system also has extended attributes. But we don't really see them a lot today because the APIs are not very useful or kind of hidden. Most of the time, if you want to do something like extended attributes, you'll use alternate data streams, which most malware analysts are probably familiar with. One place that we do see extended attributes in NT is with the Windows subsystem for Linux. So this is where you can run an Ubuntu kernel on Windows, and it uses extended attributes for things like case sensitivity and Linux file permissions. And then in SMB, there's a concept of fee and GI. So fee is a full extended attribute, that's the name plus the value. And then GI is a get extended attribute, and that's just the name. So you might issue to the server, here's a GI, I'm trying to get these extended attributes. And it will reply to you with a bunch of fee. So most theories suggest that EternalBlue was because it has a high chance of causing blue screen of death. What if it's actually a reference to IBM and Big Blue? And the whole point of EternalBlue is that NT does not properly convert OS2 full extended attributes to the newer style NT full extended attributes. So here's what the old style OS2 fee looks like. It starts with a byte. It's a flag field that can be 0 or 80. 80 just means that this extended attribute is so important that if you're going to try and copy this file to another file system that doesn't know extended attributes, generally you're going to block it or think twice about that. Next is the attribute name length, and then the attribute value length. And so after that header, you put the actual string 0, C string for the name, and then the value is not a C string, it's just binary data. But a fee by itself isn't very useful. Normally you'll find them in a fee list. So these start with a U-long, that is the size of the entire list, and then there's just each individual fee back to back. And so then you can parse this list by saying how big the size of the list is, and then going to each individual fee, seeing its size of its name, its length, and the header, and then finding the offset to the next one. The NT style fee is a very similar structure. You'll see we still have the flags field, we have the name and the value lengths. Only this time, when we add the name and the value after the header, we also align to the nearest D word pointer. This might just be because NT was trying to support certain CPU architectures where addressing offsets of pointers was difficult. So there's an extra padding. And then there's no separate list structure. Instead, we have this next entry offset at the beginning of the structure. And that just tells you the offset to the next fee in the list. So you just parse this using that next entry offset until that next entry offset is 0, and you know you've reached the end of the list. So here's an example of converting a fee from OS2 style to the new MT style. And this is a special kind of fee called the null fee. This just means that every value in the fee is 0. So the flags are 0, the name length is 0, the value length is 0, and then we need a null terminator for the C string for the name. And so we get 5 bytes of null. When we convert to the NT fee, we have that next entry offset. So we take that 5 that we had before, and then we have this new next entry offset field. So you automatically add 4 bytes, you get 9. And then you have to pad to the nearest D word. So you end up with 12 bytes total when you do this conversion. Here's our friend Trevor pointing out the actual bug for us. But instead of showing you a wall of code, I'm going to show you a wall of text. So as this function, serveOS2 fee list size to NT, iterates over each SMB fee, it accumulates the size that it needs for that NT buffer when it does the conversion, because the NT buffer is bigger. But the vulnerable line of code basically is if the start of one of those SMB fees plus the size of that fee is greater than that list, that count of the bytes of the list field, it's going to correct that count of bytes of the list field to just contain the fees that were valid. And the whole point of why did you do this? Why don't you just reject the SMB? Because the client has given us a bad fee list. The info is not matching up. But it's just important to note that this function has two outputs, two potential outputs. It can correct that fee list size, and then it also returns the size needed for the NT buffer. So the main problem here is that that count of bytes of the list was a ulong field, and when it updates that list, corrects it for us, it's casting that to a U short. So here's what it looks like on Windows XP. So as an attacker, I say my fee list here is OX 10,000 bytes. My high D word is going to be set to a 1. When it goes through and it parses the list, it's going to say, you only have E627 of a valid list. But when it goes to correct my list size, my high D word bit is not going to be changed because it's casting the size of the integer wrong. And then the size of the NT buffer is going to rely on what it thought that it's correcting the size to. But it's not, it's way bigger. So here's what it looks like in practice. This is the XP's exploit fee list. So you see we start with the CD list. We've set it to OX 10,000. We have a bunch of those null fees because they are the most efficient way to send a fee over the network and have it calculated to a big size on the other end. Then there's a filler to the offset, and then finally the Buffalo overflow fee. And the Buffalo overflow fee, the start of that fee plus the length of that fee is what exceeds our OX 10,000. So then, you know, Clippy comes along and he fixes the size of the list, and the NT fee buffer capacity can only hold up to that many fee, but we've corrected the size of the list. And this is going to keep copying one by one these fee over, and eventually it would hit unallocated space and blue screen the system. But then after the Buffalo over fee, you just send a invalid fee, and that's any fee where the flag is not a 0 or an 80, and it'll stop doing the copy there. And we'll see that come up again in a minute. But here's some assembly analysis of what this looks like in assembly code. Here's a bunch of architectures that are vulnerable to EternalBlue. These are all the point of code of EternalBlue. But most people will be familiar with x86. So you can see we're subtracting with dword pointers, and then when we do that store, we're casting it to a word pointer. And here's just an odd observation. So I mentioned earlier that I had looked at NT4 and Win2000. The NT4 Service Pack 6A SRP, basically every patch I could find for NT4, I applied it. And the latest serve.sys driver I could find was dated December 13, 2000, which is about a year newer than the Windows 2000 Service Pack 0 driver that shipped. But technically it's newer, but it doesn't have EternalBlue. So basically EternalBlue was introduced during the Windows 2000, whatever branch that was for them. So we're looking for the path of least resistance to have that vulnerable function called. That's going to come in the form of a trans2 open2. You can see in the trans2 data, it does take a vlist. So, you know, file system APIs, when you're opening a file, it also kind of doubles as creating a file. So we're going to be telling the server, I want to create a file. Here's the extended attributes for that file. We're going to be logging in anonymously, so we can't actually write files, but it's going to do that conversion before it even tries to create the file. So the permissions don't really matter. And just a side note, trans2 open2, this is a bug we saw in a Stack Overflow we saw in Samba, which is a Linux implementation of SMB. And then the FuzzBunch framework also has an exploit for this called Echo Wrecker. So here's the basic exploit process. Once we send all of our our primary and secondary transactions that contain that vulnerable fee list, the transaction2 dispatch table is going to be called. It's going to see we're trying to do a trans2 open2, and so it's going to call serve SMB open2. That's going to call the function serve os2 fee list to NT to convert that os2 style list to the NT list. That in turn is going to call serve os2 fee list size to NT, which is going to calculate the size needed for the NT buffer, and at the same time miscorrect our CD list field. Next, it's going to allocate the buffer for the NT fee on the non-page spool, but that fee buffer is going to be too small. Next, it's going to iterate over each of those fees, and eventually a RTL move memory operation is going to cause the actual buffer overflow. So this is that last step where it's just going over each fee and just copying them over, and everything goes fine until you get to that Buffalo overflow fee. And we're going to be grooming the pool to overwrite a decent structure and not just random memory. And then we stop the copy by sending that invalid fee so that we don't crash. There's another bug in EternalBlue, session setup type confusion. So there's many ways to log into SMB. At least two of them are the NT security and extended security. You can see up until the dashed line, these structures and the SMB parameter block are virtually identical. The main difference is that the NT security parameter is 13 words long, or 26 bytes, and the extended security parameter is 12 words long. And then after that, you get to the SMB data block, which contains the byte count field, which is the size of the data block that follows the parameter block. So in blocking session setup index, you can confuse this function by setting certain flags on your SMB during the login. So in this case, we're going to be setting flags 2, extended security to 0, our word count to 12, but then we're going to say our capabilities of extended security are 1. This is going to confuse the server, and it's going to look at that byte count field from the wrong place. It's going to look at it at word 13 instead of word 12 size of the count. And this byte count field is used to calculate, during the login we're sending a string containing our operating system type and also our landman type. And so it's going to use that byte count field to calculate the size that it needs to reserve for these Unicode strings. But bug 2 in a nutshell, all it really allows us to do is allocate large non-page pool memory blocks. And that's going to be useful for us for the pool feng shui. And then the nice part about it is that we can free those memory blocks on demand just by closing the socket. So we log in, session set up with the bug, and then whenever we want to free it, we just close the socket. There's another bug, and this is an oversized trans2 dispatch. So we have a problem. Bug number 1, our fee list is greater than OS 10,000 bytes in order to trigger the bug. But trans2 only allows word trans param and data sizes. And so it's not, if we just try sending trans2, we're not going to be able to send enough data to actually trigger the bug in bug number 1. So the expected SMB client behavior is that a trans is met with a trans secondary, a trans2 is met with a trans2 secondary, and an NT trans is met with an NT trans secondary. But what if we use an NT trans primary, and then we follow it up with trans2 secondaries? On the back end, the server, when we do that first NT transaction, it's going to allocate a transaction, and that transaction is then going to be expecting a data size that's greater than a word, because the NT trans allows keyword. Next, when we send these trans2 secondaries, instead of allocating a transaction, since it's a trans secondary, it's going to look up and see if that transaction exists, and it's going to find it. And then finally, when we send the last trans2 secondary to complete the transaction, it's going to execute the transaction, and it's going to see that the last command was a trans2 secondary, so it's going to go to the transaction2 dispatch table. So we can see this is exactly what EternalBlue does. It starts with an NT trans that has a total data count that's greater than OXFFFF, and then finishes off with trans2 secondaries. So we'll talk about Windows XP. Windows XP, hard to believe, but the minimum requirements for Windows XP is 64 megabytes of RAM. I think you can run Linux with 1 megabyte. Maybe even less with certain compiler flags, but it's just funny because nowadays, we just have gigs and gigs of RAM. So the exploit for Windows XP actually has to run a pre-exploit check to see if there's even enough memory to perform the pool feng shui. So it's going to just connect to the server, try a bunch of allocations, and then if those allocations fail, it won't run the exploit. It's important to note that failed exploits will leave event logs. So we have all the ingredients we need for the XP non-page pool grooming. We have our exploit, we're reopening many connections. The exploit connection is where we're going to send that NT transaction, and then the secondaries and this is just going to contain that fee list that's we've specifically set up. Next is the session setup. These are going to be the grooms and the frags. So the groom is a overflow target. It's the structure that we're going to be trying to overflow. And then frags are very similar. It's the same stuff, but they're just smaller, and that's just to fill in memory gaps. So one thing that's different about Windows XP is that the non-page pool, the allocator here is going from higher addresses to lower addresses. So we're going to be going from right to left in this demonstration. But we start with a pre-exploitation memory layout. There's just random stuff in a fragmented pool. Next, we're going to send that NT trans primary and every trans2 open to secondary except for the last one. So we're not triggering the bug yet, but all we need to do is just send one more SMB, that last trans2 secondary, and then the bug will trigger immediately. So we send all of our fee list except for the last little bit of it. Next, we start sending these frag buffers using the session setup bug. And these are just small. They might leave some gaps in memory, but it doesn't matter. And then we're sending the actual groom buffer. So this is the stuff that we actually want to overflow using the same session setup bug. And we just send a bunch of these to fill up memory. And then finally, we send that last trans2 open to, and that causes the OS2 to NT conversion to happen. And then we do overflow into the adjacent groom. So here's a graph of, on the x-axis is the event. An event is either an allocation or a free. And then on the y-axis we have addresses, going from high to low. And then that dashed line is just separating the pre-exploit memory check from the actual exploitation. We can further subdivide this to see where those frag allocations just to fill in random memory slots are, and then where the grooms are. But what's really nice about this is that we are seeing patterns with the memory grooming. So the NT allocator, in OS design, you want really tight allocations, and that's exactly what we're getting. So here's the actual target of our Buffalo overflow. So we talked about that client OS type and client landman type strings that get allocated when we do the session setup bug. At the beginning of that allocation, the serve.sys driver is going to add this serve pool header. And so this only has two fields, it's just the allocation size, and then a pointer to a pointer of a look-aside list. So this look-aside list is a very common pattern seen in Windows for interlock change heaps. Basically, when we overflow this pointer, we can swap whatever pointer we put there, we can swap whatever's at that pointer with the address of our serve pool header, which is where we started our overflow. So we're looking for a function in the kernel that we can, has a fixed address that we can put into that field when we overflow. Luckily, on Windows XP, or unluckily, the boot processor control region starts at a fixed address. And then on all 32-bit versions of NT, the processor control block is at a fixed offset from the processor control region. And then inside of the processor control block, at a fixed offset for Windows XP, is the processor power state. So we can pre-calculate those offsets and that fixed address. We know that at this memory address, we're going to find the processor power state. And the processor power state has this really nice function. It's the idle function. It's called a bajillion times a second. Basically, all this function normally does is start interrupts and halt the processor. But in our case, we're going to be swapping that function with our overflow. So when we overflow, we set the allocation size to EB06. That's a jump OX8. And then we set the look-aside list field to that address that we pre-calculated. So now, when the address of the idle function gets swapped with our header right here, it'll jump over the look-aside list and into the main shellcode stage, which we sent during the overflow. And so Windows 7 is a completely different exploit. A lot of things have changed from XP. One thing that Windows 7 fuzz bunch exploit does is that it simultaneously exploits x86 and x64. So the structures that we overflow actually, the offsets of things are such that it can overflow and target x86 and x64 at the same time, which is pretty cool. Another thing that changed was the non-page pool allocation direction. So now sequential allocations, we're going from low to high addresses, or left to right. Windows Firewall was technically introduced in XP, maybe even earlier. At least the GUI came in XP Service Pack 2. It doesn't really matter in most configs, such as joining a domain, you're going to get your port 445 opened up. NT 6.0, the HAL heap is still static, but that boot processor's control region is not, has been ASLR. So that means that the idle function, we don't know, we can't pre-calculate where the idle function is. So we can't really use that methodology anymore. And then also with Windows 7, now we have SMB2. So it used to be that the networking, all the network code was part of the serve.sys SMBv1 driver. With SMB2, they introduced a new driver, serve2.sys, and they kind of moved all the networking out to a library driver called servnet.sys. So that's just important to note. So we're going to be opening many connections when we groom the pool. We're going to have our exploit connection. That's going to contain the fee list. That's going to overflow. Then we're going to have use the session setup bug again, this time to create what are called allocation and hole connections. And then this time our grooms, instead of being those session setups, we're going to be trying to overflow a servnet.sys network buffer. So that when servnet.sys sees that it has a packet coming in, it will allocate a buffer with some headers, and we're going to try and overflow those headers. And the fuzzbunch exploit makes these look like they're SMB2 packets, but it's actually at a point where servnet.sys has not delegated responsibility to serve or serve2.sys yet, so it's a fake SMB2. And the only thing that I've seen that might be a good reason for this is it might be an IDS bypass because people aren't monitoring SMB2 as much, and we're eventually, after we overflow these buffers, we're going to have to send the shellcode over these same connections. So again, we start with the pre-exploitation memory layout. We have random stuff in the pool. This time we have servnet.sys for those network buffers. It has look-aside memory. We're going to send all of our fee list except for the last trans to secondary again. And then now we're going to start sending grooms. So these are just servnet.sys buffers that we say are real big. We got an SMB coming. Next, we send what's called the allocation connection. So we're sending that session setup bug. We're just going to make this a little bit smaller than what our goal NT fee buffer size is. Next, we're going to send the whole buffer connection, which is the same size as the NT fee buffer size. We free the allocation connection by closing the socket. Now it's able to just allocate whatever random memory it needs in that slot instead of interfering with our grooming. And then we send the final groom packets, and we're hoping that one of those will come after that session setup whole allocation. We free the whole allocation, close the socket, and now a buffer that is the same size as that NT fee buffer that's calculated is now available. But then during the conversion process from OS2 to NT fee, that NT fee buffer was not the right size. So here's the target of our Buffalo overflow this time. Like I said, when you tell the servnet.sys driver, when you open the TCP connection and you send your net BIOS headers, you say, I have an SMB coming, it's this big. It reserves that much memory to hold that SMB. And so there's a bunch of fields in this, but the ones that we're really interested in are this MDL. So an MDL is a built-in structure in Windows NT, memory descriptorless. All they do is map virtual to physical, non-contiguous. It just basically, whatever we overwrite here, we can build a write what where primitive because we can set the map system virtual address to wherever we want. So when we overflow, we're going to set it to the HAL heap, which is just non-ASLR, read, write, execute memory. So at this point, anything that we write on that socket is going to look at that MDL where it's supposed to be writing that to. You can see it used to point to the actual buffer, but now it's pointing to the HAL heap. So now we're going to send the shellcode over each groom connection that we opened. We're not sure which groom actually got overflown, so we have to send the shellcode on all of them. We also overwrite that servnet winsock struct, the winsock context, and that will that servnet winsock struct has a function table in it. So now when we free all of the groom connections after we sent the shellcode, that function table has a cleanup function in it, and we just point that to the double pulsar shellcode. When we get execution this time, we are running at dispatch level, so things like paged memory are off limits, and that's going to be necessary for double pulsar to use in order to backdoor the transaction to dispatch table. So a quick and dirty way to get from dispatch level to passive level is to hook the syscall MSR register. At this point, we are violating patch guard, and if the patch guard timer comes along and sees that we have hooked the syscall table, it could blue screen the system. But we're only going to have it hooked until the next system call. So the next system call happens. We run our stage 1 shellcode that just calls double pulsar. returns and then restores that syscall MSR back to what it was before, and hopefully patch guard hadn't run, and we can go on. So EternalBlue on 8 Plus has changed a little bit more. So by default, anonymous logins to the inter-process communications tree is blocked, but many misconfigurations still allow anonymous logins. So we need that anonymous login in order to say we're creating a file in order to send that exploit fee list. The other thing that we'll notice that's a very big difference is that now when we tell servnet.sys to reserve us a buffer, it's going to put the headers of that buffer after the buffer. So on Windows 7, the headers are before the buffer. On Windows 10, they're after the buffer. And this means we have to overflow a lot more memory in order to overwrite the MDL and things that we need to overwrite. So there is a higher risk of crashing with Windows 10 and Windows 8 and up. Another thing is that the HAL heap, where we stored our shellcode last time, has now been marked as non-executable, so it has dep. So we're going to need a dep bypass for where we want to store that shellcode. So Stéphane Lebert published gave a presentation called Bypassing Windows 10 Kernel ASLR Remotely. So we know that the HAL heap still has no ASLR, but it's marked as dep. But the x64, the AMD 64 page table entry for that page is also not ASLR. So we know where the page table exists, page table entry for that. And at bit 63 is where the actual NX bit is set. So in order to bypass this, we're going to have to run the exploit basically twice. The first time we overwrite that MDL to point at the page table entry, and then we just send 1 byte over the socket with a 0 so that it overwrites that NX. And then we pretty much just do the same methodology as the Windows 7 exploit after that. So here's the outcome. So here's the major differences between XP and Vista Plus. You'll see the vulnerability was during that list size calculation where it miscorrected the pointer size, or the integer size when it cast the pointer wrong. Next, the overflow happened during the OS2 fee to NT, so as it was iterating over each fee. On XP, the target was that serve pool header, which we hijacked with interlock free. Our shellcode was sent when we overwrote that pool header, and then the function we hooked in order to get code execution was pop processor idle. And then in Vista Plus, we're overflowing. Our target is that servnet receive buffer header, and then we hijacked execution during that common receive handler that looked into the function table for the cleanup function and called back. We stored our shellcode on the heap, the HAL heap, using a write wetware primitive. And then finally, to get code execution of double pulsar, we hooked the system call table. So here's what the patch looks like for EternalBlue. Insert OS2 fee list size to NT. Before, we were casting to a short on that long field. So the fix is you just cast it to a long when you fix it up. But again, why are you fixing the client's broken fee list? If the fee list is bad, just reject the whole SMB, and we wouldn't have been here in the first place. Next is the session setup type confusion. So this allowed us to allocate memory and free it on demand. This line's intentionally left blank because as far as I can tell, it still exists. But it's not really that big of a problem. If you want to reserve a lot of memory on SMB, you don't need this bug. SMB is just very insecure with the way that it allocates memory, so you can pretty much denial of service any system that you can see. Next is the patch for the oversized trans2 dispatch. So this is where we sent the NT trans primary and then followed it up with trans2. So now when a transaction is allocated, there's a new field called secondary command, or at least that's what I'm naming it. a lot of this stuff you can get from the debug files, but things like the structures you can't, just the function names. So they've added this new field on a transaction structure allocation where they store what they're expecting the next follow-up secondary transactions to be. And then when it goes to look up that transaction, it sees if the incoming SMB's command matches that secondary command. If not, it returns null. So there's some next-gen mitigations that are available today. We've seen the server service, landman server. Its permissions have been revamped a number of times. So nowadays, anonymous logins are blocked by default. We've also witnessed in the past year the death of SMB v1. NetPile finally got it through. All new versions of Windows 10 that ship do not have SMB v1 disabled or enabled. You have to go in and screw around and get it enabled, which is a little unfortunate because we have the results of a 30-year NSA pen test. I think we've got all the bugs ironed out now. SMB v1's good to go, right? Another thing is that the serve.sys driver and the NT kernel have been audited over time to be adding more depth and non-executable bits. We also finally got fuller, not full NT ASLR, but with Windows 10 Redstone 1, we've got those page table entries for the depth bypass. Those are now randomized. And then in Redstone 2, the HAL heap is also randomized. And then we also have some newer mitigations that are a little bit harder to turn on, but are really cool. They're mostly designed, I believe, for the Xbox DRM, but one of them is HyperGuard. So this prevents us from touching the syscall MSR. So getting from dispatch level to passive level, you can't just hook the syscall table anymore. There's a hardware enforcement that stops you from touching those syscall MSRs. And that's because the whole NT kernel is now running in a hypervisor. Another thing is kernel control flow guard. All those function pointers that we overrode to get code execution, if this is enabled, those will be double checked before those function callbacks are executed, and bug check will happen if you overflow and change one of those hijacks. So we have some next-gen mitigations that are coming tomorrow. One of them is hardware shadow stacks. So stack overflows, this will finally, hopefully, be the killer. Every time you call a function or put something on the function return stack, there will be a shadow stack that contains that, and then whenever you return, it'll double check to make sure that that return address is right. So this kills things like ROP, COP, those kinds of things. So we didn't see a stack overflow in here, but some of the other internal exploits like Eternal Champion, that is a stack overflow. This also means that we'll have to redesign some shellcode. It's not going to stop shellcode, but you just have to think about things like ROP and COP and whatnot. Another thing that has no real public info besides this one tweet that Matt Miller of the Microsoft Security Resource, whatever it is, he tweeted at me after my DEF CON talk, and he said that they were adding a pool allocation order randomization. So those nice patterns that we saw for the grooming of the pool, those are going to be theoretically randomized. So that's a good area of research for anyone interested in something cool that's coming to Windows. Because, like I said earlier, OS design likes tight allocations. It doesn't want to deal with fragmentation during critical allocations and things like that. And so it's going to be weird to see what they've done. Finally, I just have some extra resources here. I think the best resource on here is the second one. It's Warwick Wang's GitHub. So he's written in Python pretty much all of the internal exploits. And so if you want to look at them at a code level, that's the way to go. Number 5 there is my DEF CON talk, where I talked about not just EternalBlue, but more of all of the internal exploits, more of a breadth versus depth talk. And then finally, I just want to say thank you to Nicholas Jolie, PG Boy, Warwick Wang, Alex Yanescu, Matt Miller, Matt Swish. And that's all I have. time for questions.
We have time for a few questions. If you're not saying your questions, please exit quietly out the side door.
No questions.